Hello gentlemen, welcome to today's discussion. Today we will be discussing about the few facts about the induction motor. That is generally the three-phase induction motor. These windings, these phases are wound in the stator. And what is the frequency of that? F is equal to Pn by 120. That means P is the number of poles per phase, N is the RPM of the magnetic field produced, and F is the frequency in cycles per second. RPM of the machine, what is the RPM? N is equal to 120 F by P. So say if the number of poles is 6 and F is 50 Hertz, so if F is 50 and P is 6, then N will be equal to 120 into 50 by 6. That is equal to 1000. So N is 1000. So what is this N? Existing only for the RPM of the rotary magnetic field. Otherwise, it is not existing anywhere. So, this is the first interesting factor. First interesting fact about the synchronous, about the induction motor. Even if this is called the synchronous speed. So, this is speed at which the magnetic field rotates. These three wires are coming from the power station, and in the power station so this is R, this is P, this is Y. Similarly, in the power station, this is R, this is B, this is Y. So, how that power is being produced is that in the presence of these windings in the stator, let us think that the windings are done here. Okay, now here in the rotor, a strong magnetic field, permanent magnet. This is the permanent magnet, or this is the magnet which is excited from within the system of the machine. That means it is excited from a attached small PMG. So what is this synchronous speed? It is the is the speed at which the magnet is rotating. That means it is the speed at which the fluctuations of the current in these separate windings are taking place. Or here at the consumption point of the power, the currents are changing in these all the three wires, in these all the three windings in such a way that the synchronous speed of the magnetic field generated here, it is same as that of the speed of this magnet here. This has to be always north and this end is always south. It is rotating like this. As it rotates, it does not change its polarity. It remains north and south all the time. As it cuts the windings, it produces an EMF, and that EMF is used here, which is producing the magnetic field of this magnetic field. So this magnetic field will be rotating at such a RPM that it is equal to the RPM of this magnetic field here. So this synchronous speed, it means that the RPM at which the magnetic field at the source is rotating, provided we make the number of poles same as here, 120 F by P. If we change the number of poles, supposing it is having a number of poles equal to 12 number of poles, okay, and here we change the number of poles to 6. So what will be the synchronous speed? Then synchronous speed is N is equal to 120 F by P. So here we have reduced the number of poles. So then the synchronous speed will be greater because the poles number has reduced. So if the generator here is moving at say 900 RPM, here the synchronous speed will be double of that. That means 900 into 2, that is 1800. So the synchronous speed here will be 1800. So there is one fact about the induction motor. If we increase the number of poles, then say if we increase from here from 12 to, if we increase from 12 to 24, then the synchronous speed will reduce. That means the speed at which this field is rotating, it will be produced here at lesser speed. So that is the meaning of the synchronous speed. And one more interesting fact, this is about the synchronous speed. As the name synchronous speed suggests, synchronous means it must be synchronized with something. That means at the same speed with the power station. That is the meaning of the synchronous. Synchro is same. So the magnetic field of the motor, it will be at the same as that of the power station if the number of poles are same for both. That is the meaning of the synchronous speed. And let us see what is the frequency of the current passing through in the rotor. Frequency of the current will be Pn by 120. Number of poles is fixed. Now it will depend upon the n. So what is this n? We have seen that the rotor falls behind the synchronous speed by some percentage. That means the rotor is never rotating at the synchronous speed because the rotor is having a very high load. So it will be rotating at a different speed, say Nr. This was the rotor, and the synchronous speed is Ns. So there will be a difference in the speeds between these two. The difference between the synchronous speed and the rotor speed, it will give us the north south. If this is the magnetic field which is cutting the conductors of the rotor, then the speed at which this magnetic field is cutting the conductors, it is responsible for the frequency of the rotor current. So what will be that speed? That will be the speed of the synchronous speed of the stator magnetic field minus the speed of the rotor. So say this Nr will be how much? 0.95, say 0.96 ns. So the difference in speeds will be, that means equal to 0.04 ns. So it is very less because the rotor is also trying to catch up with the stator magnetic field. Frequency will be equal to P ns. Here it is not ns, it is 0.04. 0.04 ns by 120. So what is that? 0.04 into Pns by 120. That means what? What is this? This is the normal frequency, say 50 Hz. So this will be multiplied by 0.04. This will be equal to 2. That means the current in the rotor will be having a frequency of only 2 Hz. It is not believable, but it is true that the rotor current frequency is very less. Whereas the stator current frequency is 50 Hz or 60 Hz, but the rotor current frequency is very less. How the reversing of the motor can be done? Say this is R. If they are connected in this way, and the motor is turning in clockwise direction. Then for reversing, what we have to do? We simply have to interchange any two phases, either this phase, these two phases, or these two phases, either B and Y or R and Y, or even R and B. Here, then the reversing of the motor can be possible.